Yes, but you don't want to see these lines. I try and avoid it through methods of perfection. That's blind you all. That and my shins are beat to hell. Like it's an atrocious looking knot. Both neuralgia and extraction and scar connections, but I got knots all up in front of my shins like another model. Okay. Fundamental theorem of calculus. Two versions, right? I've got the version we did for dot one, simple intervals. Take the antiderivative, look at the ends. I've got the line integral version. The line integral version says, take the antiderivative and look at the ends. And then because of that, I know that the only way I can do this, the only way I can find this generalized antiderivative is when I have a conservative vector field. So this is the problem with the fundamental theorem for line integrals. So if I don't have a conservative vector field, what am I going to do? Well, I really don't just want to think about this for open curves. I really want to think about this for closed curves, because that's the more interesting case. So let's consider a closed curve. Let me add a simple closed curve. What did the word simple mean when I talked about closed curves? For all t except for a and b, right? So the only place you get the hit a point twice is the start end point. So this curve doesn't cross itself, except where it closes back up. Well, then there's an inside and an outside to my curve. If I have a simple closed curve, I can think of cutting a piece of paper along that curve, and I'll have a hole and a thing I cut out, right? And the thing I cut out will be one piece because the curve never crosses. I want to decide on a direction to walk that curve. I'm going to say that my curve is positively oriented if the finite region bounded by C. Okay, so I think of the piece I cut out, right? That's the inside of the curve. That's the finite part, not the part that goes off to infinity, is on the left as I walk around the curve. All right, wait just a freaking minute here. Here's my curve C. If I am standing on the edge, picture a little person standing on the edge of the curve. Which way are they facing? If they start to take a step forward and the inside of the curve is on their left hand, which way are they walking? Are they walking this way or are they walking this way? I'm going to go that way, aren't I? As I walk, my left hand will be on the inside of the curve. So this direction that's the positive orientation. Hey, wait a minute. If my curve is just a circle, there's my curve, it's a circle. Which direction is the positively oriented version? Clockwise or counterclockwise? Isn't that the way we define the trig functions to go around? When we say we go in the increasing direction of t, we're going counterclockwise. Same definition, we're just calling it a positive orientation. Okay, okay. I'm going to use this to try and answer my question. I can only do this version of the fundamental theorem when I have a conservative vector field. I also know that if I have a conservative vector field, what happens when I integrate on a closed curve? I get 0. Because the starting and ending point are the same. And that means R of B, F of R of B and F of R of A are the same. Thing minus itself is 0. Yes. That's what our independence of path ideal was. If we had a closed curve, a conservative vector field always gave me an interval of 0. Notice I haven't put what C is. All C is just closed, right? It could be that some of our integrals are 0 anyway, but every closed curve gives me a 0 when it's conservative. What if it's not conservative? If it's not conservative, then I need to actually do the integral the hard way. That's going to suck, especially if C is something ugly, right? I don't want to think about what the parametrization of this curve is going to look like. That's nasty. But then I go back up here to the fundamental theorem of calculus. The fundamental theorem of calculus says to look at the end to figure out what's going on across the whole interval. The fundamental theorem of calculus says I can do some evaluation in the middle, or I can look at the antiderivative on the ends. This says I can do the evaluation on the end, or I can do it all around the curve, right? But when I have a closed curve, I have an inside and an outside. So what if instead of thinking about a curve and an end, let's think about the region inside my curve. D is the finite region bounded by C. That finite region that we were talking about in the previous definition. Now, we're going to use a term quite frequently. We'll write a boundary of, and I apologize in advance. I hate the fact that I'm going to reuse a symbol. I'm going to use my partial derivative symbol. The boundary of my region is called the partial of it. I don't know why. I got stuck with this notation. I'm going to deal with it. If I want to think about the fundamental theorem says you can look at the middle by looking at the edge. I want to go across the interval from A to B. I do the integral. I can look at the edge, A and B. What if I think of doing the integral in the middle instead of doing the integral on the edge? George Green came up with the following. I forgot a word. A simple, closed, positively oriented, smooth curve. Smooth? Oh, right. It's got continuous partial derivatives. And let D be the finite region bounded by C. If P and Q are C1, continuous, and their first derivatives are continuous, on the open region containing C and D, then the integral over C of f dot dr, wait a minute, that's the work, yes? That's the same as the integral p dx plus q dy. Instead of doing the integral on the curve, I can do the double integral in the middle. dA. Of what? Of the partial derivatives, qx minus py. What the absolute is this? Wait a minute. How did I know whether or not my vector field was conservative? Yesterday. How did I decide whether or not a vector field was conservative? But those were the x, y, and the yx of the potential function, right? Which meant they were the first derivatives of the p and the q. If py is equal to qx, then my vector field is conservative. That means this is 0. What happens when you integrate 0? Oh, come on. What's the integral of 0? Every time. Ben, what did you ask me earlier? If it's conservative, this is going to be 0. no matter what I'm doing, this integral is going to be 0. But if my vector field is not conservative, then this tells me how not conservative it is, how far off from being conservative. And so the lack of conservation is encapsulated not on the edge, but in the middle. And this is a double integral. I know how to do double integrals. I don't have to parameterize. That makes my life a crap ton easier. If the region I am integrating on is easy compared to doing the parametric garbage around the outside, then it's probably easier to do the double integral than the line integral. I'm going to apologize a little, but this problem is absolutely nightmarish when I write it down on purpose. Not just no, hell no. I want you to imagine what it would take to do this in parametric form. I need a parametric equation for this circle. What are the parametric equations for this circle? Almost. So it's 2 cosine and 2 sine. The radius is 2, yes? It would be x squared plus y squared equals 4. So that makes x equal to 2 cosine t and y equal to 2 sine t, 0 less than or equal to t less than or equal to 2 pi. So in order for me to do this problem, I need to take this x and this y and plug them in up here. Then I need to take the derivative of 2 cosine t, put it here, the derivative of 2 sine t, put it here, and do the integral from 0 to 2 pi. I want you to think about that means we're going to have e to the inverse tangent of 2 sine t. Do you know how to integrate that? I'll be here for a month. This is a horrible thing to deal with. But I say to myself, I say to myself, wait, this is a line integral. As a line integral, I'm integrating on a circle. The inside of that is a disk. If my area is a circle, and I'm integrating inside that circle, I can do that in polar coordinates. Matter of fact, it would be a lot easier to do it in polar coordinates, wouldn't it? But doing stuff in polar coordinates is a doubling. I'd be integrating on the inside of the circle, as opposed to on the edge of the circle. But that's exactly what Green's theorem tells me I can do. I can convert a line integral into a double integral. So in this situation, D is the disk of radius 2, centered at the origin. Describe that to me in polar coordinates. So far, so good? If I use Green's theorem, I can convert the integral on C to a double integral on D. The thing I need to know is, first of all, what am I integrating? Oh, I do my partial derivatives like I was going to do to check if this is conservative. I need qx minus py. Okay, I go back up to my line integral. What's p? What's q? I'll go back up to my statement for Green's theorem. What's p? What's q? Ah, so all of that junk in that first set of parentheses is p. All of that junk in that second set of parentheses, that's q. What's qx? Five. Because in terms of x, this is a constant, which means its derivative is zero. How about py? Because in terms of y, this is a constant, its derivative is zero. In other words, I have to do the double integral over my disk of 5 minus 2 dA. And you just told me a couple seconds ago, that's my disk. You're doing the double integral of 3. I'm doing it in polar coordinates because I'm doing a disk. What goes here? Don't forget your Jacobian. And then I'm going to do my integral from 0 to 2 and from 0 to 2 pi. Ta-da! There's an even faster way to do this that doesn't actually require me to do the integral. From here, I can say that this is the double integral of 3 dA over the disk, right? That makes that 3 times the area of the disk. What's the area of a circle? The radius of this circle is 2. By the way, if you do the double integral, guess what you get? 12 pi. Because you get a 2 pi here, and then you get r squared over 2. 2 squared is 4 over 2. That's 2 times 3, that's 6 times 2 pi. I get 12 pi. A really disgusting, damn near impossible line integral became an absolutely trivial double integral. before I actually try and do this problem, I've got a curve. I'm going to do a line integral. I should make the parametric version of the curve. Let me draw the picture, see what it looks like. So what is this picture? I'm going to with me so far? Okay. Here's the section I'm graphing, and it says C is the boundary of this, which means I'm thinking about the bounded section of the plane. That's just this little bit right here. From x equals 0 to wherever these cross looks like 3, I think. Let's hit the trace button and check. Yes, they cross at 3. So I'm going to zoom in a little. This is my curve, but it's in two pieces. And if I want to go around this positively oriented, I've got to go this way and then this way. I've got to go counterclockwise. So I've got to go down the sloped part and up the curved part. We had such fun coming up with parametrizations for curves, didn't we? But if I think of the area inside this region, that's a type 1 region as a double integral. It's got a curve on the top, a curve on the bottom, number on the left, number on the right. It would be a lot easier to do a double integral than it would be to do the half integral, wouldn't it? So this is a perfect case. I have a simply connected region. I have functions that have nice different derivatives. And I have a nice description for my region. Let's use Green's theorem. I need to know what I'm taking the integral of, and I need the description for D. The other joys of warm weather and shorts is allergies. So, first question. Do you want to do the integrand or do you want to do the region? We got to do them both. Pick one. We'll do that one first. Okay, that's qx minus py. How do I remember it's qx and py? Well, if I think of my vector field, p is first, q is second, right? So I take the opposite derivative to get the Clairaut's theorem, right? P is normally in the x spot, so I need py. Q is normally in the y spot, so I need qx. X comes before y, do the x derivative first, the y derivative second. Qx minus py. So here's p, here's q. Qx is 4x minus py is 3x. Yes, it's always qx minus py. P goes with the x part. So I'm going to take its other derivative. Q goes with the y part. So I'm going to take its other derivative. And it's the x derivative before the y derivative. So qx, then py. We'll have another way of remembering it come Monday. Now, what's my description for the region? No. Bottom to the top, left to right. So I'm going to do this integral, dy dx. Ta-da! But the best part is I know how to do that integral. And I didn't have to parameterize squat. With a little bit of work, you should leave yourself some space. The answer is 6.75. Question. When Green worked on this, it was the early 1800s. One of the more interesting results of this is an actual practical tool. If I want to measure the area inside a region, the area of D is the double integral over a D1 dA. Right? But according to Green's theorem, if D is a nice, simple, quote unquote, region, then I can switch between the inside and the edge. I could turn this into a line integral as long as qx minus py is equal to 1. Well, how could I make qx minus py equal to 1? I could say, oh, well, we'll just let q equal x and p equal 0. And if I do that, Green's theorem tells me this. P dx q dy. There we go. Instead of measuring the actual physical area, I can measure around its edge. And I can figure out the area that way. I am going to go measure a lake. I have an overhead picture of the lake from a satellite. How do I measure the lake? I measure its edge. A physical tool was invented to do this. A plane polarimeter. Sorry, a polar planimeter. I always get that screwed up. Pole, because we put this pin down and it acts like a polar coordinate origin. and then we take this pin and we trace it around the edge of our curve, and it does Green's theorem. There's a picture in our textbook, page 1099. A planimeter measures area by measuring edge. And it's literally using Green's theorem. And there are this particular article was written in March 2020. It's a history of the polar planimeter. And there are dozens of different kinds that all basically work the same way. It's just how the linkage actually does the integral itself. By the way, this is not the only way to do this. I could just as well say I'm going to let P equal minus Y and Q equal 0. And then this becomes the integral around the boundary of my region of minus Y dx. Each of those gives me the area of the region D by never measuring the area itself, by only measuring the boundary of it. My favorite use for this is in ultrasounds. How big is this object inside this ultrasound picture of your insides? But an ultrasound actually highlights the edge of a region very well. So all I have to do is trace the region's edge, and I know how big something is. By the way, another common version of this formula adds these two together. But that would give me twice the area, so they put a 1/2 in front of it. Those three formulas appear on page 1099, same page with the picture of the planimeter. Questions? What happens if my region is not simply connected? Here is a punctured region. I have my kidney shape, and there's a hole in the middle of it. And my region D is only the area between the two things. I still want to think about the boundary, but the boundary is now two curves, right? I have this outside piece, curve 1, and I have this inside piece, curve 2. But if I want to put a positive orientation on these curves, I walk around C2. Which way? Positive orientation means the region is on my left hand as I picture myself walking around that little circle. If I'm walking around that little circle and D is on my left, what direction am I walking? But if I go counterclockwise, then D, the shaded region, is on my right side, isn't it? I'm walking around this circle. Here I am standing right at this point. In order to go around C2, the positive direction, I have to be walking clockwise. Here on the outside, I'm going counterclockwise. But here on the inside, I got to go clockwise to do the positive orientation game. Crap. Okay, here's my problem. This region is not simply connected. Green's theorem does not apply. I have an idea. I need a sword. I want you to cut this region horizontally, right across the middle of that circle too. I'm going to draw a line right across the middle of this circle. Chop. With me so far? Now, I want you to consider that piece. Look at the shaded region above the red lines. That's simply connected, isn't it? Green's theorem applies there. So I would go around the top half of C1. I would go across this left line. I would go L1 this way. I'd go around the top half of C2. I'd go around line 2 this way. And I'd make a simply connected region, wouldn't I? That works. Green's theorem can now be done on the boundaries instead of in the middle. That's only half the game. What about down there? That's also simply connected, isn't it? So I go around the bottom half of curve 1. I go right to left along this line. We called that line 2. I'd go around the bottom of curve 2. That's the correct direction. I'd go across line 1 this way. Wait a minute. What happens when you go backwards across the same curve? What happens when you go across the curve one way and then across it the opposite way? When I turn my curve around, I get a minus sign, don't I? So going from left to right on line 1 is canceled by going right to left. Going left to right on line 2 is canceled by going the other way. These should cancel each other out. What am I left with? The integral on curve 1 and the integral on curve 2. But the integral on curve 2 is backwards, isn't it? It's clockwise, not counterclockwise. So if I turn that integral around, I could subtract instead of adding. You can extend Green's theorem to go around more curves. All you have to do is cancel appropriately. And then we do the integral this way. Notice the orientation. Counterclockwise on the outside, but clockwise on the inside. And then we just add the two results together. Yay! There's an example here on page 1101, example 5. Walks through this idea. So I can even do this when I don't have a simply connected domain by cutting it up into simply connected domains and then gluing it back together to avoid the problem. The other interesting thing about that multiply connected rather than simply connected, we call it a multiply connected region, is it can reinforce to me how critical my partial derivative ideas are. notice that in this problem, those two curves are oriented the same way, aren't they? The function in this problem is y over x squared plus y squared plus x over x squared plus y squared. Sorry, minus x over x squared plus y squared. There's only one place where that entire integral is effed up. That's at the origin. 0, 0 is going to make this break, isn't it? 0, 0 is going to screw that up. That means everywhere else, this is conservative. But at the origin, it isn't. This curve goes around the origin. When I integrate this curve around that little circle using a line integral, I get 2 pi. When I integrate around this curve, I also get 2 pi. Why? Because that vector field is conservative between those two curves. And if it's conservative between those two curves, my line integral should be 0. But only when I do the chopping part, right? Because I need to be simply connected. That means the outside integral has to be positive 2 pi, and the inside integral has to be negative 2 pi. But that would make this one go clockwise instead of counterclockwise, so the minus sign comes into play, and they're both the same. They're both 2 pi. My independence of path idea applies wherever my vector field is conservative, even when I go around points where it isn't conservative. We call this idea deformation of path. And that's why a lot of times it's just easier to say, no, screw it, I'm going to integrate on a circle. Because between the two curves, it's nice and easy, and I can squeeze it down. You should read through the examples in this section. I guarantee you, I only did a couple of them. You should do more of them. Tomorrow is question and answer again, because this is a lot of, and that gives you the whole weekend to work on this. But then I'm going to ask the same question about vector fields, but instead of asking about two-dimensional vector fields, I'm going to ask about three-dimensional. Because I want to be able to turn this idea from a 2D concept to a 3D concept, because I live in a three-dimensional world. So how do I know when a vector field is conservative in 3 dimensions? How do I know what the integration on a closed loop in 3D looks like? What's the inside of a loop in 3D? We have to talk about that. That's next week. Tomorrow, questions for 16, 3, and 4. I will see you all then. I want you to understand that the sections in this chapter, the three main integral theorems that we're going to do, are so well known and so popular and so impressive. One of my coworkers at the University of Pittsburgh, who's now at IUP, has been tattooed on these tabs.